what are some insights you've gained over those 5-6 years of autopilot about the problem of autonomous driving? So you leaped in having some sort of first principles kinds of intuitions, but nobody knows how difficult the problem.
I thought the self-driving problem would be hard, but it was harder than I thought. It's not like I thought it would be easy. I thought it would be very hard, but it was actually way harder than even that. So, I mean, what it comes down to at the end of the day is to solve self-driving, you have to solve. You basically need to recreate what humans do to drive, which is humans drive with optical senses, eyes, and biological neural nets. And so, in order to that's how the entire road system is designed to work with basically passive optical and neural nets, biologically. And now that we need to, for full self-driving to work, we have to recreate that in digital form. So we have to, that means cameras with advanced neural nets in silicon form, and then it will obviously solve for full self-driving. That's the only way. I don't think there's any other way.
But the question is, what aspects of human nature do you have to encode into the machine, right? So you have to solve the perception problem, like detect, and then you first realize what is the perception problem for driving, like all the kinds of things you have to be able to see. Like what do we even look at when we drive? There's I just recently heard Andre talked about at MIT about like car doors. I think it was the world's greatest talk of all time about car doors.
Yeah.
The fine details of car doors. Like what is even an open car door, man? So like the ontology of that's the perception problem. We humans solve that perception problem, and Tesla has to solve that problem. And then there's the control and the planning coupled with the perception. You have to figure out like what's involved in driving, like especially in all the different edge cases. And then I mean, maybe you can comment on this. How much game theoretic kind of stuff needs to be involved, at a 4-way stop sign? As humans, when we drive, our actions affect the world. Like,
sure,
it changes how others behave. Most autonomous driving, if you're usually just responding to the scene, as opposed to like really asserting yourself in the scene. Do you think?
I think these sort of control logic conundrums are not the hard part. Let's see.
What do you think is the hard part in this whole beautiful, complex problem?
So it's a lot of friggin' software, man. A lot of smart lines of code. For sure, in order to have create an accurate vector space. So, like you're coming from image space, which is like this flow of photons, going to the cameras, and and then so you have this massive bit stream in image space, and then you have to effectively compress a massive bit stream corresponding to photons that knocked off an electron in a camera sensor, and turn that bit stream into vector space. By vector space, I mean like you've got cars and humans and lane lines and curves and traffic lights and that kind of thing. Once you have an accurate vector space, the control problem is similar to that of a video game, like a Grand Theft Auto or Cyberpunk. If you have accurate vector space, it's the control problem is I wouldn't say it's trivial. It's not trivial, but it's not like some insurmountable thing. But having an accurate vector space is very difficult.
Yeah, I think we humans don't give enough respect to how incredible the human perception system is, to mapping the raw photons to the vector space representation in our heads.
your brain is doing an incredible amount of processing, and giving you an image that is a very cleaned up image. Like when we look around here, we see, like, you see color in the corners of your eyes, but actually your eyes have very few cones, like cone receptors in the peripheral vision. Your eyes are painting color in the peripheral vision. You don't realize it, but their eyes are actually painting color, and your eyes also have like this blood vessels and all sorts of gnarly things, and there's a blind spot. But do you see your blind spot? No. Your brain is painting in the blind spot. And you're going to do these, like, see these things online where you look here and look at this point, and then look at this point, and if it's in your blind spot, your brain will just fill in the missing bits.
So cool. The peripheral vision is so cool. It
Yeah.
makes you realize all the illusions for vision science. It makes you realize just how incredible the brain is.
The brain is doing a crazy amount of post-processing on the vision signals from your eyes. It's insane. So, and then even once you get all those vision signals, your brain is constantly trying to forget as much as possible. So human memory is perhaps the weakest thing about the brain is memory. So because memory is so expensive to a brain and so limited, your brain is trying to forget as much as possible and distill the things that you see into the smallest amounts of information possible. So your brain is trying to not just get to a vector space, but get to a vector space that is the smallest possible vector space of only relevant objects. And I think, like, you can sort of look inside your brain, or at least I can, like when you drive down the road and try to think about what your brain is actually doing consciously. And it's conscious. It's like you'll see a car because you don't have cameras. You don't have eyes in the back of your head or the side. So you say, like, you basically your head is like you basically have like two cameras on a slow gimbal. And what's your and eyesight's not that great. Okay, human eyes are, and people are constantly distracted and thinking about things and texting and doing all sorts of things they shouldn't do in a car, changing the radio station. So having arguments, is like, so then, like, say, like when's the last time you looked right and left, and and rearward, or even diagonally, forward, to actually refresh your vector space? So you're glancing around, and what your mind is doing is trying to distill the relevant vectors, basically objects with a position and motion, and then editing that down to the least amount that's necessary for you to drive.
It does seem to be able to edit it down or compress it even further into things like concepts. So it's like it goes beyond, the human mind seems to go sometimes beyond vector space to sort of space of concepts, to where you'll see a thing. It's no longer represented spatially somehow. It's almost like a concept that you should be aware of. Like if this is a school zone, you'll remember that as a concept, which is a weird thing to represent. But perhaps for driving, you don't need to fully represent those things, or maybe you get those kind of indirectly.
You need to, like, establish vector space and then actually have predictions for those vector spaces. So, like, like if like you drive past, say a bus, and you see that there's people. Before you drove past the bus, you saw people crossing, just imagine there's like a large truck or something blocking sight. But before you came up to the truck, you saw that there were some kids about to cross the road in front of the truck. Now you can no longer see the kids, but you need to be able. But you would now know, okay, those kids are probably going to pass by the truck and cross the road, even though you cannot see them. So you have to have memory. You need to remember that there were kids there, and you need to have some forward prediction of what their position will be.
It's a really hard problem.
At the time of relevance.
So with occlusions and computer vision, when you can't see an object anymore, even when it just walks behind a tree and reappears, that's a really, really, I mean, at least in academic literature, it's tracking through occlusions. It's very difficult.
Yeah, we're doing it.
I understand this.
Yeah.
So some of it,
It's like object permanence. Like same thing happens with the humans with neural nets. Like when like a toddler grows up, like there's a point in time where they have a sense of object permanence. So before a certain age, if you have a ball or a toy or whatever, and you put it behind your back and you pop it out, if they don't, before they have object permanence, it's like a new thing every time. It's like, whoa, this toy went poof, disappeared, and now it's back again, and they can't believe it. And that they can play peekaboo all day long because the peekaboo is fresh every time. But then we figure out object permanence. Then they realize, oh no, the object is not gone; it's just behind your back.
Sometimes I wish we never did figure out object permanence.
Yeah, so that's
So that's an important problem to solve.
yes. So like an important evolution of the neural nets in the car is memory across both time and space. So now you can't remember. Like you have to say, like, how long do you want to remember things for? And there's a cost to remembering things for a long time. So you know, like run out of memory if you try to remember too much for too long. And then you also have things that are stale if you remember them for too long. And then you also need things that are remembered over time. So even if you, like, say, have, like, for argument's sake, 5 seconds of memory on a time basis, but, like, let's say you're parked at a light and you saw, use a pedestrian example, that people were waiting to cross the road, and you can't quite see them because of an occlusion. But they might wait for a minute before the light changes for them to cross the road. You still need to remember that that's where they were, and that they're probably going to cross the road, type of thing. So even if that exceeds your time-based memory, it should not exceed your space memory.